What is up, guys? My name is Neil. This is the first video on the channel. Hopefully, I will continue to make more after these. Yes, I'm making this video because this problem was kind of annoying. Yeah, and I heard a lot of other people had problems with it. But I guarantee you this problem is so stupid. It's really simple. It's just you need to be careful with your bookkeeping, and you need to be careful with certain mistakes that you could possibly be making. All right, let's get right into it. So as you can see, we have this point right here. Wait, I'm gonna actually do this thing. We have this point right here, and we have this arm, and the arm is fixed, right? Where does that say that? Yeah. They remain perpendicular to each other, so that means that this arm is fixed in this position throughout the entire thing, right? So what does that mean? That means that this distance right here stays constant. So we're already getting into something or the other, right? So we've got this thing that's spinning around, and we've got this thing that's sort of accelerating upwards, right? It's like at a certain speed upwards right now, it's at an angle right now, and it's accelerating upwards at the same time while it's spinning around in this circle. So you can already see that there's this angle and there's this angle, right? I'm sorry, this angle and this angle. And you have a fixed distance from the origin. So this is already sort of screaming spherical coordinates, right? I don't know why the textbook, like, they have a step-by-step way of going through this problem and they solve it in cylindrical. I personally think that's a very stupid approach. You should solve this thing in spherical. All right, so let's solve this thing. So what do we have? So we have this angle, right? So the first mistake that I feel like people would fall into is using this angle, right? Because this is the angle between this arm and the horizontal, right? But the distance r, if you're using spherical, the distance r is actually at a different angle from the horizontal. It's at like this angle right here, right? So you sort of want to figure out what the angle between this side of the triangle and that side of the triangle is, and do beta minus that angle. So I'm going to show you what I'm trying to say. So I'm going to draw this arm as some sort of triangle. So I'm going to draw it. It looks like, and then like that, and then like, right? And so we have this sort of triangle. I don't know, it doesn't actually look that much like a triangle. I'm trying to use this iPad to draw well, but whatever. And we have 200 millimeters here. We have 300 millimeters here. So what's the length of this third side? Well, you would use Pythagoras theorem, and you would say that the length of this third side is 300 squared plus 200 squared whole root, right? And that is equal to, let me put that in my calculator in 1 second. That is 360.55. So I'm going to round that to 5.6. So it's 360.56 millimeters. Right? So that's the third side. And I know you don't need the length of this side to calculate this angle. You can just use the tangent. But I'm gonna calculate it anyways because we're in spherical and I want to know this distance right here. This distance r, right? Because it's probably gonna be that in my spherical calculations. So now I want to know what the angle between r and the horizontal is, and I'm gonna name that angle phi. So this is the angle phi, and this is the angle beta, and this angle right here I'm gonna call alpha. And the relation between alpha, beta, and phi is that beta plus phi equals alpha, right? But you can sort of see that from my drawing here, because alpha is this big angle right here, like that. And this is phi right here. Oh my god, that is a terrible drawing. Anyways, this is alpha. So we have this relation. And now looking at this triangle, knowing that this is a right angle, we have that the tangent inverse of 200 over 300 equals alpha. So what is alpha? And we're going to do this in radians because I'm going to solve this entire problem in radians. And I'm going to explain to you why. That was actually the main problem that I had when I was solving this problem. I just was solving it in degrees and I was like, oh, my calculator's in degrees. Like, why am I getting this thing wrong? Well, it turns out that the circumference of a circle, that is such a bad circle. Okay. The circumference of a circle, right, is 2 pi r. It is not 180 r. So you gotta be in radians. And anyways, yeah, so we have alpha is tangent inverse of 2 by 3. So I'm gonna do that. That gives us alpha is 0.588 radians. Right? So that's alpha. Right now beta is 30 degrees. So beta is 30 times pi over 180. And this cancels and uses pi over 6. I'm just going to simplify that. 1 is pi 6. 0.524. About 0.524 radians. So phi is I'm actually going to define this angle from the horizontal. So I'm going to go up beta and then down alpha so that I get the downwards from the horizontal. So I'm going to go alpha. I'm going to fix my equation here to say that phi equals beta minus alpha. That's not alpha. So what is beta minus alpha? 0.524 minus 0.588. So I'm going to put that in my calculator, figure out what that is. And what I get is negative 0.064. So I'm gonna save that. Now we have a value for phi. Now, if phi is beta minus alpha, and I take a derivative of like, if this is this minus this, and I take a derivative of this with respect to this is sort of like a constant. So this is sort of just gonna die, right? Because I mean, also this thing doesn't change. Like that angle between this side and this side stays constant. But the angle beta does not stay constant, and neither does the angle phi. So I'm gonna take derivatives, and I'm gonna say that the derivative of phi is equal to the derivative of beta, which is 10 degrees per second, which is 10 times pi over 180, which is pi over 18 radians per second. So now we have the angular velocity of phi. I'm gonna do the same thing for the angular acceleration. The angular acceleration is 20 times pi over 180, which is pi over 9 radians per second squared. All right, so we're getting some values. So we have all the sort of derivatives with respect to phi. Now we have that the robot is revolving at the constant rate of 40 degrees per second. So that's nice, because if this thing is revolving at the constant rate 40 degrees per second, we don't actually care where it is. I don't think we care where it is, honestly. They also just didn't give us where it is in terms of the angle theta, from the x-axis, right? So it doesn't actually matter where it is, because if it's spinning at a constant rate, no matter where it is, like here or behind it or on the left or on the right, it sort of still is spinning at that rate. So the acceleration, I feel like, just won't be affected, no matter what the value of theta is. So I'm just gonna say theta equals question mark, because we don't know where it is, and frankly we don't care. We do care about the derivative of theta, and that is w, or omega, and that is 40, because it's in radians per second, guys. Again, remember this. Okay, so 40 times pi over 180, which is, what is it? It's this guy times 2, which is 2 pi over 9 radians per second. Okay, so we have another expression, and we also know that since it's at a constant rate, the angular acceleration of theta is 0. So there we are. What else do we need? We have r. Since r is staying at a constant value, the speed in the r direction is 0, and so is the acceleration. Not in the r direction. That was worded poorly. The rate of change of r is 0, and the rate of change of r is also 0. But just because this is 0 does not mean that the speed in the r direction is 0. There still could be a speed in the r direction. and there still could be an acceleration in the r direction, and we're going to see that. And it's because of chain rule, right? When you take derivatives, they sort of blow up, especially here. So they are asking for the magnitude of the acceleration of p, right? So how would we do that? We need to find the acceleration in all three coordinate directions. So we have an r direction, right? The r direction would be outwards this way. We have a phi direction, which would be upwards this way. Let's sort of zoom in here. And then the acceleration in the theta direction, since theta is like sort of spinning around that way, is going to be into the page. Right, so it's going to be like that. And frankly, whether it's into the page or out of the page does not matter, because there's no acceleration of the angle in that direction, and also because we're taking the magnitude. Yeah. Ignore what I first said. It doesn't matter because we're taking the magnitude. That's the reason why it doesn't matter. Anyways. So we need to find the three components of the acceleration. Now, the acceleration, I'm going to start with the acceleration in the, I'm going to start with this formula actually. Acceleration is acceleration sub r in the r hat direction. Acceleration sub in the theta hat direction plus in the phi hat direction. So this is our acceleration, right? So first we need to find the acceleration in the r hat direction. And that is the acceleration of the value r, so the second derivative of r, minus r times the first derivative of phi squared, minus r times the first derivative of theta squared, times the cosine of phi squared. And the reason why you have this cosine squared phi, so this makes sense, right? Because this is just acceleration. So this is just, right? This is just acceleration. It's the second derivative of displacement, right? This is the equivalent of w squared r, right? It's like how you get how it exists in uniform circular motion. And the reason why it's negative is because this this right here is like, if you have a circle, you have it'll be the acceleration outwards, while the sort of, if you have a circle and this is the radius and you're over here, your r double dot will be positive in this direction, while your r phi dot squared will always point this way, and that's why you subtract it, because these two accelerations sort of cancel each other. Same thing with this guy right here, but the thing is, you're adding that third dimension of phi, right? And so this thing could be, if I flatten this circle, imagine this line is the circle, and we're looking at this thing from this angle now, and this is where this is phi, right? This would be like x, and this would be y. And right now this is x, and this is z, right? So right now, if it's spinning into the page, if it's all the way up, like if this is where the point is and it's spinning around like this, there's actually no acceleration because it's literally staying in the same point. You know what I mean? So the cosine of this angle phi matters because you start spinning as soon as you tilt down from that axis right there. And now if you're spinning into the around this thing, now this point actually is spinning. Anyways, that's a side note. I'm gonna try and get through this video without deriving all of this stuff because that should be something I do in another video. Anyways, so this is your formula. So what is r double dot? R double dot is 0 minus r times phi dot squared. So phi dot is not 0 if I remember correctly. Yeah, it's not 0. So you have r, which is 360.56. I'm just going to use millimeters for this whole thing. Times pi over 18 whole squared. And then we have minus r theta dot squared cosine squared phi. So we have 360.56 times theta dot, which is 2 pi over 9, times the cosine of phi, which is negative 0.064. And this thing is squared. And so that will give us, put in my calculator, and then negative. Okay, so I'm getting negative 185.9 millimeters per second squared. So that would be our acceleration in the r direction. Now, I don't know, I might have made a calculation mistake, but we'll find out eventually because I do have the answers here somewhere. Okay, so next comes the acceleration in the theta direction. So, and that is equal to cosine phi over r times the derivative of r squared theta dot minus 2r theta dot phi dot sine phi. Now, I'm going to take this derivative. So the derivative of r squared theta dot is, I'm going to first start with the r squared because it's product rule. So we're going to go d by dt r squared theta dot equals 2r r dot theta dot plus r squared theta double dot. Okay, so that whole thing, and that is multiplied by cosine phi over r right here. And so that means that I can cancel some r, so this dies and this dies. And now we have cosine phi times 2r dot theta dot plus cosine phi times theta times r times theta double dot. Okay. So that whole thing is then added to minus 2 r theta dot phi dot sine phi. So what does that mean? If we look at r dot, we know that this thing isn't changing in radius, so r dot is 0. So this whole term goes to 0. Now we know there's no angular acceleration in the theta direction, because this speed stays constant. So this goes to 0. So we're left with this term. Now what is that term? We have negative 2r theta dot phi dot sine phi. So our r is 360.56. So that's times theta dot, which is 2 pi over 9, times phi dot, which is pi over 18, sine phi, and phi is negative 0.064. Okay, so now that will be equal to times 360.56 So the answer I'm getting is 5.62 millimeters per second squared. Okay. Now, for the last term, which is the acceleration in the phi direction. Oh yeah, another common mistake I've seen is a lot of my friends didn't expand this. So yeah, you should definitely expand your things, because some unexpected stuff always shows up with the product rule. Anyways, the acceleration in the phi direction is equal to 1 over r times the derivative of r squared phi dot plus r theta dot squared sine phi cosine phi. So let's expand this derivative. So we have 2r r dot phi dot plus r squared phi double dot, right? And this whole thing is over r, so that becomes 2r dot phi dot plus r phi double dot plus r theta dot squared sine phi cosine phi. And now we know that that r dot is 0, so this goes to 0. This does not go to 0 because r phi double dot, neither of those are 0, and this does not go to 0 either. So let's plug in. So we have 360.56 is R, so we have 360.56. I'm actually going to take that out because it's common to both of these terms. And find double dot, what is that? It is pi over 9 plus theta dot square. Theta dot is 2 pi over 9 whole squared times sine phi cosine phi. Sine 0.064 cosine 0.064. And then I'm going to close this big bracket, and that should be it. So I'm going to plug that in. Okay. So I'm getting 114.64 millimeters per second squared. And so for the magnitude of the acceleration at that point, I'm going to square all of these terms. This one, and this one. And I'm going to add them up and then root it. So it's going to be 114.64 squared plus 5.62 squared plus 185.9 squared. And this negative sign doesn't matter because I'm squaring it. And the acceleration should be so my answer right now is 218.48 millimeters per second squared. I'm gonna check with what the book has. Yep, they have 219 millimeters per second squared. So yeah, I mean, they just rounded, I guess, in some places where I didn't. So this is the correct answer. Yay.